video. And I'm starting the screen sharing. All right, let's try to see if it will work this time. All right, do you see the screen?
Yes.
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 Thanks. All right, the topic of today's lecture is chemistry of technetium. And this nuclide has an extraordinary role in nuclear medicine. 15 years ago, big pharma company did not consider any new radiopharmaceutical if it was not labeled with technetium. Nowadays, it's probably closer to fluorine 18. What is special with technetium? Actually, it has nothing to do with its chemical properties, something to do, of course, with its nuclear properties. But it's a daughter of a nice mother. It is known that nuclear fission results in typically generation of two fragments. One has a mass approximately 1/3 of mass of uranium, and another has a mass of 2/3. So which results in two peaks of products. One with a mass around 100 and another with a mass around 130. And you might recognize that strontium-90 was one of dominant nuclides in Chernobyl fallout, iodine-131 at initial step, and then cesium-134 and 137. So there are very massive products. One of the products is molybdenum-99. And this radionuclide decays with a half-life of 66 hours, well, 65.94 to be exact. And it decays to technetium-99M, which is metastable radionuclide, which further decays by isomeric transition to ground state. Half-life of technetium is convenient. You have time to perform labeling, deliver to the lab radiopharmaceutical and inject into patient and give some time to distribute radiopharmaceutical. Nice gamma line, 140 kilo electron volt, which means that it is not very much scattered inside the body, but also does not require heavy collimator. So standard name of collimator for technetium and gamma cameras is low energy, high resolution collimator. It also does not generate many conversion or Auger electrons, which means that local dose for technetium-based radiopharmaceuticals very low, very benign. We can have a look later on. But what is important is so-called transient equilibrium situation between molybdenum and technetium. Strictly speaking, word equilibrium is not really fortunate because equilibrium generally considers reversible process while radioactive nuclei is not reversible. But when you have two nuclides, one mother and one daughter, and daughter is generated by decay of mother, the decay of mother is determined by simple exponential decay law. The accumulation of daughter nuclide is determined by this formula, which is a solution of differential equation. And in this formula, lambda 1 and lambda 2 are decay constant of mother and daughter respectively. What is important that if you even separate completely at certain time point the daughter from mother, it starts to form again and reaches the maximum of activity, which is equal to activity of mother nuclides in roughly 3 half-life. So in this way, the activity of daughter nuclide is growing. Interestingly, that if you separate completely daughter nuclide from the mother, its accumulation starts all over again before it would reach the activity of the mother nuclide in the time point, according time point. So you could, in principle, have a mother nuclide as a source of the daughter nuclide. And importantly, this source is independent to a high extent on presence on site of cyclotron or reactor. Here is a scheme of one of the most commonly used generators. Such generators are produced in Tomsk as well. The construction might be a little bit different, but the core of the system is column made with typically aluminum oxide, where molybdenum is absorbed in the form of molybdate ion. If you elute this column with normal saline, so 0.9% sodium chloride, mother remains to be absorbed on the column. But daughter, technetium 99, is eluted with a saline. So our German colleagues from East Germany suggested very nice system with vacuum vials. So they simply autoclave the vials in the presence of water vapor at temperature 120 degrees centigrade, and then at the high temperature they just seal this vial with a rubber stopper. So when such a vial cools down, water or vapor condense, and that is under pressure in such a vial. So typically generator construction contain a needle, well, some bacterial filter in one needle. You put the reservoir with saline, and on the other needle, you place a vacuum vial. So under pressure requires sucks in saline from the eluent vial. Saline goes through the column and elute pertechnetate in the vial. So you get a source of radioactivity which you could repeatedly elute from the mother nuclide. Molybdenum is relatively easy to elute or to produce. Nowadays, it's of course a special uranium target which is irradiated, and the processing of uranium is very well known due to nuclear fuel cycles. So big factory all over the world produce molybdenum, load the generator and ship all over the world. 66 hours, it's a good half-life which permits delivery all over the world by air freight, and the cost is cheap as dirt. One standard 34 gigabecquerel generator of technetium costs the same money as indium for 2 patient doses. And with such generators, you can run tens and probably hundreds of patients. So this is the biggest advantage. Low cost, favorable dosimetry, nice gamma, well suitable for gamma camera, and half-life permitting labeling and clinical investigation. Well, it's a nice feature of technetium. But unfortunately here, the nice feature ends, and chemistry of technetium is a nightmare. So we discussed earlier chemistry of indium, chemistry of lutetium, chemistry of gallium. They all are 3-valent metals in water solution. It's easy to handle them. If you take technetium, it's possible to have 8 different oxidation states. Each of them have its own coordination number, so from 4 to 6. And the most common oxidation states are +7, +5, and +4, but the stabilization at certain oxidation state depends on the reduction condition. Well, in principle, you can use technetium as a pertechnetate. So it's a monovalent anion, and it mimics iodide, so it cheats sodium iodide's importer, so you can study the function of thyroid gland using pertechnetate or diagnosticize well-differentiated thyroid cancer. But generally speaking, pertechnetate ion is inert, does not interact with organic molecules, so you have to reduce it. And when you reduce pertechnetate, the oxidation state of the product depends on several factors. It depends on reducing agent. You could use a variety of it. It depends on chelator, in presence of which reduction takes place, and chelator might stabilize technetium in one or another oxidation state, and it might depend on reaction condition. Studying of technetium chemistry is not easy. There is no such thing as stable technetium. It's extincted radionuclide. So the name technetium actually stress its artificial nature. There is, of course, ground state, which is extremely long-lived nuclides, and big pharma company had some milligrams of technetium each, which enable them to study the macrochemistry of technetium. Cost a lot of money. And what has been shown that if you, for example, reduce pertechnetate with sodium metabisulfite, then the product is technetium O2 hydrate, with is technetium 4. This reaction, unfortunately, very common in technetium chemistry. So if you don't control, you end up in this oxide. And this oxide is famous or inglorious reduced hydrolyzed technetium colloid, which is byproduct of reduction. And if your labeling is not optimized, it present in radiopharmaceutical. The problem is that it does not, it's not water soluble, but amount of this compound is too little to form a precipitate. It forms a colloid, and manifestation of presence of colloid is typically accumulation in liver, in spleen, and to a certain extent in bone marrow. So this is our enemy. However, if you use the same reducing agent, but in the presence of D-thiochelator, technetium would be stabilized in form of technetium ore, which has oxidation state of 5. So it's a different compound. If you use another reducing agent and another ligand, you could reduce it down to technetium 1. So the reaction condition and chemical environment determine the fate of technetium during reduction. So that's all about technetium chemistry. So it's difficult to control or difficult to predict oxidation state and stability of technetium complex, because it depends on many subtle factors. But there is a bright side of it, that in principle it provides a lot of opportunity to modify structure and properties of technetium complex, and later on today we will a little bit discuss about these opportunities. Generally speaking, we need somehow systematize technetium chemistry, which is not easy, and to describe different complexes of technetium. A notion of a core of technetium has been introduced. Reduction of technetium often results in formation of technetium which is bound either to 1 or to 2 oxygen atoms from actually the mother pertechnetate, or in some cases it might oxygen can be substituted by a nitrogen atom. So those complexes are quite stable, and then further ligands could be added to this core. And one distinguish, for example, technetium O core, which contains central atom, technetium, oxygen, and, well, in principle, 4 different ligand electron donors placed around. Depending on the nature of the electron donors, one could have different names. For example, if in this case the Y's are sulfur and N are nitrogen, one would say S2N2 complex. And then this, the surrounding, chemical surrounding, might have a different form. They might be connected to each other, they might be not. So very common in radiopharmacy is a SN3 core where there is a complex of technetium O core where one atom is sulfur and 3 other atoms are nitrogen. It might be alternative technetium O2 core where 2 oxygen are connected to technetium. So initial charge of the core is then 1+. And again, it might be different atoms. It might be phosphorus, it might be sulfur, in some cases it might be oxygen, nitrogen. So again, when coding by donor atom, you might have P2 and 2 complexes and so on. This is also very common core in radiopharmaceutical chemistry. And here is the structure of N technetium N core. Again, it's very interesting that those complexes have pyramidal shape, so ligands are located in equatorial plane, and in this case, oxygen atom or nitrogen atom just protrudes over the equatorial plane of the complex, and in the technetium O2 core, the oxygens are located above and below equatorial plane, forming B pyramid. Relatively recently have been discovered 2 new cores. One is technetium tricarbonyl. So in presence of strong reducing agent and carbon monoxide, technetium forms a complex which contain 3 carbonyl group, which are very tightly bound to technetium, and 3 waters, which can be relatively easily substituted by other elements. This has been developed by Roger Shibli as master examination work under supervision of Roger Alberta in early 90s, and it's actively used in different chemistry. Another core, which is also relatively new, it's so-called Heineck core. And Heineck stays for hydrazine nicotinic acid. It's quite unique in this sense that there are evidences that this chelator is monodentate, which is very unusual in coordination chemistry, though there are still some evidences that it might be not whole truth, and either this nitrogen or electron donors from surrounding acids could contribute to stabilization of high-NIC core. What is interesting that since it's mono or at the best bidentate chelator, so it requires colligands, and you can modify physicochemical properties of the whole complex by modifying chemical nature of chelators, of colligands, adding or reducing the charge of the whole core or its lipophilicity. And finally, in some complexes, technetium is just naked without oxygen or nitrogen or so to just fit in the system. One talks also about naked technetium core. Structure of technetium complexes is important, though I have to say that the most commonly used radiopharmaceutical in at least oncology is a complex of technetium with methylene diphosphonate, and structure of this complex is still unknown. So in early 60s, it was found that this MDP goes actively to bone metastasis. So that time it was enough to register as radiopharmaceuticals. And now nobody wants to put a lot of money in metastable technetium to figure out the structure of this complex. So the most commonly used radiopharmaceutical has no known structure. Nowadays, it's completely unthinkable. Moreover, people working in regulation and compliance claims that nowadays registration of technetium generator would be impossible if it would be a new invention. Too many uncertainties with it. We will discuss a few core and we will briefly discuss well-known and established radiopharmaceuticals, as well as a little bit about our research in technetium chemistry. So one of workhorses in nuclear medicine is technetium or core, having 3 positive charges. So it's 5+, and from chemical point of view, important that is stable in the presence of strong chelating agents in aqueous media, which means that if we manage to put technetium ore in our radiopharmaceutical, it would be stable in the blood. And this is a precondition for successful clinical application. So it forms square pyramidal complex with tetradentate chelators, including N4, which means that donor atoms are for nitrogen, might be amide at nitrogen, N3S, so 3 nitrogen, 1 sulfur, or N2S2. One is important radiopharmaceutical is HMPAO or Ceretec, which is used for diagnosis of abnormalities of cerebral blood flow. So apparently if we have trauma or we have stroke, it results in severe disturbances in brain blood flow. So if we can visualize these disturbances, we could estimate the extent of the damage. So in this case, we using N4 complex, nitrogen in equatorial plane, oxygen is protruding above, and you could see that there are plenty of aliphatic carbons around. So neat intuitively, you could conclude that this substance should be very lipophilic. And it's neutral, so it's non-charged lipophilic. That means that it can penetrate through the cellular membrane, and even more, it can penetrate through blood-brain barrier, hematoencephalic barrier. So, and distributed inside the brain initially proportionally to regional blood flow, apparently. So what happens next is that this complex is challenged by glutathione, which exist abundantly in a human brain. And technetium is very thiophilic. It loves to form complexes with SH groups. So it just challenges and steals technetium from the complex. So technetium got fixed in the area behind BBB where it was delivered. So that enables visualization of distribution of technetium, which is proportional to blood flow. So it's a nice chemical or medicinal chemical work, which complex charge, desirable lipophilicity, and desirable stability, which permits to remain stable in the blood flow but be challenged behind BBB. Another example is competitor of Ceretec. It has a commercial name, Neurolite. It's again technetium or core. In this case, this is N2S2 complex. And you also could see a lot of aliphatics around, which makes it pretty lipophilic. Which means that, again, it can penetrate blood-brain barrier. However, the fixation mechanism is completely different inside the brain. So in brain, there are plenty enzyme with esterase activity, which disrupt esters here. So what happens inside the brain when it's distributed? So these esters got cleaved And instead of neutral and lipophilic moiety, we got here carboxy group. And carboxy group is heavily, well, charged reasonably, and we have two. So charged compound cannot penetrate blood-brain barrier, so they got fixed again in the position where it has been delivered initially. So here is a very good example. Here is imaging of stroke using neurolight, and apparently even we could see here this area where the brain is damaged and is not supplied properly with blood. Well, here is alternative approach for measurement of regional blood flow is Doppler MRI, which shows also area with diminished blood flow. But they are not equivalent completely to each other. Yet another important technetium pharmaceutical is Techniscan or MAG3. MAG3 is mercaptaacetyl, this moiety, and 3-glycine. So it's essentially 3-peptide where mercaptaacetyl moiety is coupled at the N-terminus. It is charged, carry single negative charge, so it's water soluble. It does not penetrate for this reason through vessel wall. What is important that this compound is secreted or excreted through kidney proportionally to kidney function. So insufficient secretion means that kidney is not functional. It is easy to produce. So reduction of technetium takes a few seconds at room temperature. Chelating takes more time. And the reason is that we need to deprotonate amide nitrogens, and they are not really well deprotonating. So for this reason, when working with this kind of chelator, you need either have quite high pH, about 11, or you need to have a high temperature, and possibly you need add also intermediate chelator to stabilize technetium in right oxidation state in the right complex. But that in principle works, and works very nicely. And here is an example of study of kidney function, and you probably could see that some accumulation of activity is in both kidneys, but one is apparently damaged while another only is working, and clinicians could get even quantitative measure of kidney function and understand the degree of damage, and probably use this imaging for monitoring of therapy outcome. For us is very interesting that that kind of complexes are essentially peptides. They're easy to incorporate into structure of peptide during peptide synthesis. So it's 3-peptide plus mercaptoacetyl at N terminus. And there were quite a number of reports of the use of MAG3 as possible chelator for technetium labeling of peptides. So when we start to work with antibody molecules, we wanted to evaluate the MAG3 as a possible chelator for technetium. Antibody molecules have 58 amino acids. Well, that means that they are amenable for peptide synthesis, and presence of MAG3 requires peptide synthesis to be sure that the mercaptoacetyl is placed exactly on N-terminal moiety. We did labeling. It was reasonably stable. We have demonstrated the specific targeting in ex vivo experiments, and we had a reasonable tumor to non-tumor ratio. So in the end, we went to our Department of Nuclear Medicine to make a beautiful picture of gamma camera, which demonstrates that uptake is specific, because if you have tumors which are non-blocked, you have a good accumulation of activity in tumors, and if you pre-saturate with non-labeled antibody, there is no uptake of radioactivity. This image we got. A problem is that we figure out a huge activity in abdomen, which we have not been detected in our initial development. It turned out that this is a blind gut appendix, or, well, blind gut because appendix is only part of blind gut. So in rodents, blind gut is functional. They need it for digestion of cellulose, which is a major part of their food. So therefore, in rodents, whatever is excreted through bile into gastrointestinal tract got initially arrested in the blind gut. In human, appendix is rudimentary, so they generally would be distributed all over abdomen. And this is a trouble, because first it would create a high background for imaging of extrahepatic abdominal metastasis. For the first, even worse, this activity might form clumps in gastrointestinal tract that might rise false positive finding. So we need something to do with it. In mice, 24 hours after injection, this activity was gone. I doubt that it would happen in human, and 24 hours is not a good time point for technetium. So what you do if you run in hepatic uptake or hepatobiliary excretion? Usually, both hepatic uptake and hepatobiliary excretion are associated with lipophilicity. There are several mechanisms which are responsible for uptake of lipophilic compound to liver. Where it typically by hepatocytes is metabolites, and then fate of metabolites depending on the physicochemical property. They might be either trapped inside the liver or be excreted through bile in gastrointestinal tract. So our first step was to increase hydrophilicity. We make it cautiously, substituting one by one glycine, which are pretty lipophilic, by serine, which are hydrophilic. They're polar. They're not charged. What we have found that substitution of single serine, a glycine by serine, reduce twice activity which excreted into gastrointestinal tract. This is total activity. And when we substitute all three, so it was threefold reduction. And if you look at this image of mouse, we still can see here the blind gut or cecum, but now tumor is more bright than blind gut. So this indicated that we are on the right track, but still we are far not happy with these results. So we try to make even more potent hydrophilizing of the complex. And in this time, we used, instead of serine, glutamate, which is negatively charged and accordingly much more hydrophilic. In principle, one might use either aspartate or glutamate, but in fact, aspartate is very bad for peptide synthesis. So one never see these aspartic acid in synthetic peptides, so preferably it's glutamate. Here was very pronounced effect, more than threefold decrease of activity in gastrointestinal tract, and we reduced from 30% down to 5% the activity in the case of triple substitution. So my 3E completely obliterated activity in gastrointestinal tract, nearly completely, but at a cost of high retention of activity in kidney. So activity which didn't go to liver and to bile was anyhow excreted via kidney. Afibody molecules got reabsorbed, and apparently 3-glutamate variant was very highly residualizing label, as we discussed earlier. So it retained to very high extent in kidney, which from clinical point of view, much better than activity in gastrointestinal tract. First, it's easy to interpret this image. Kidney have very well defined shape. And second, the kidney metastases are very, very seldom. So you most likely will not miss metastasis because of uptake in kidney. Well, still, we wanted to see if we can reduce kidney uptake while keeping the gastrointestinal activity low. So we looked for this by combining serine and glutamate. And what we have found very interesting, so it's again MAEEE uptake in kidneys around 100% of injected dose per gram. If we use variant with serine, glutamate, or glutamate, serine, they were absolutely equal, and activity in kidney was reduced more than twofold. But when we used variant containing mercaptoacetyl glutamate, serine, glutamate, so exactly the same amino acids but in a different order, the kidney uptake was reduced further, nearly twice compared with counterpart. It's completely excluded that it's experimental artifact. That was once upon a time a product candidate for company Affibody AB. So we repeated this experiment 4 times with 4 different independent batches of mice. It came to exactly the same result. So indeed, the sequence of amino acid inocculator plays a very important role. And here we could see that in this mouse image, activity in tumor is approximately equal to activity in kidney, and there is no activity in gastrointestinal tract. Well, that was interesting. That was, I think, our essential structure properties relationship finding, which permitted rational design of technetium-based radiopharmaceuticals. So to be scientifically rigorous, we also evaluated influence of positively charged amino acids. So from hydrophilicity point of view, lysine carrying at physiological condition single positive charge is as hydrophilic as glutamate, but charges are different. What we have found, interestingly, that if we have mercaptoacetyl serine, lysine, serine sequence, we had a quite low gastrointestinal tract activity, while slightly highish kidney, approximately at the same level as with ESE sequence. But if we used 4 lysines, so the activity in kidney went up, but also activity in liver was very significantly increased. And in this study, we made a clear connection between positive charge of peptide, particularly N-terminus of Affibody molecules, and elevated liver uptake, which was essential structure properties relationship finding. And here is example how labeling chemistry influence the biodistribution. So we modifying here maximum 3 amino acids, and we have very different biodistribution profile with this compound providing reasonably good sensitivity and specificity of imaging, because it's high contrast, it's low uptake in normal tissues, and initial construct, well, essentially non-functional from diagnostic point of view. So labeling chemistry plays a very important role in development of imaging agents. Okay, we talking now for 55 minutes. I don't know about you, but I would probably appreciate 5 minutes break. Should we decide to meet again in 5 minutes?
Yes, of course.
All right, great. Okay, then 5 minutes and we meet again. I hope that everybody is back. Could you please show you up to show that you are present? Okay. I hope that other ones who are not there are back. So let's continue. All right. So there were other effects of substitution of amino acids in the mercaptoacetyl containing chelators. So if this complex of technetium is unstable in vivo, you have very clear manifestation. First of all, I mentioned that technetium is thiophilic. It loves SH groups. And in our blood are plenty of proteins which carry free cysteines, unpaired cysteines. So instability is often manifested in elevated blood activity, which is no good, of course, because the blood is everywhere. It contributes to background during imaging, and it reduces contrast, tumor to non-tumor ratio. I mentioned that pertechnetate accumulates in organs which express sodium iodide importer. And its stomach, its thyroid, and its salivary gland, which have noticeable overexpression sodium iodide importer. And instability of complex often manifested by elevated blood, elevated stomach uptake, and elevated salivary gland. So when we working with technetium, we always include in our biodistribution measurement of activity in those organs to find the possible instability. We had uptake in stomach and salivary gland in case of MAG3. It was not awfully high, but it was visible. So that indicated that our complex was not completely stable. What is interesting, that when we included one serine in the complex, we have quite dramatic reduction of radioactivity in blood at the same time. And these measurements has been done, so to speak, head-to-head in the same batch of mice, so to avoid batch-to-batch variability in animal physiology. So was a clear reduction of activity in blood, but also in stomach and in salivary gland. This effect, at least for stomach and for salivary gland, was even more pronounced when we had 3 serine here instead of 1. So digging into literature suggested that side chain might stabilize a complex because as we discussed earlier, the chelator complexes are always reversible. So that means that probably at certain moment, the connection between technetium and amide nitrogen got broken. And this is a vulnerability moment. So it might happen that technetium will start to transchelate to some other blood protein and form unstable complex. So when we have electron donating side chains, we pick up the technetium and give it time to re-establish the bond, dative bond with amide nitrogen, and in this way stabilize it. And since effect is apparently dependent on number of serine, it very clearly could be ascribed to action of serine. Similar effect we have seen also in the case of the use of glutamate. Again, addition of single glutamate reduces activity in blood, stomach and salivary gland, and this effect was clearly proportional to amount of glutamate in the complex. So we can stabilize our complexes and we can modify the biodistribution profile by selecting right amino acids. I like this approach to labeling. So it permits clear incorporation of chelator during peptide synthesis. It's simple. You just extend N-terminus with mercaptoacetyl and probably with a few amino acids. You could modulate complex stability by selecting appropriate amino acids. You could modify charge and lipophilicity of side chain, and in this way modify of whole Affinity molecules physicochemical properties. Disadvantage is that pretty harsh labeling conditions, it's temperature of 90 degree typically, or you need to have pH above 11 for labeling. And since you need site-specifically introduce mercaptoacetyl to N-terminal nitrogen amine, so it's possible for peptide synthesis, it's impossible for recombinantly produced peptide. But in principle, it works. We currently working on very different class of targeting compounds. It's peptide, decapeptide, bombazine, which can be used for imaging of prostate cancer. And we hope that at certain moment, we will make a clinical translation research in Tomsk with it. Well, as I mentioned that mercaptoacetyl has its limitation. It's not encodable. So this means that it's only peptide synthesis, and if you using recombinantly produced protein by biotechnology, it's no way to go. So it would be interesting if we could substitute mercaptoacetyl by amino acid, and in principle, at N-terminus, if you place cysteine, you could also have SH group. And presence of thiol is essential for site specificity of the labeling. It is believed that technetium or core initially binds to SH group or 4 SH group of 4 different peptides, which stabilizes it +5 oxidation step and technetium or core, and then one of peptide start to replace one by another other ligand and make a monocomplex. So in principle, presence of N-terminal cysteine is homologous to N-terminal mercaptoacetyl, but homology is not complete, because if we form technetium in the middle of the complex, in case of mercaptoacetyl, technetium forms a number of 5-member cycles, technetium and C and technetium. The same here, technetium and C technetium, and here is technetium SCCN. What is magic that angles in these cycles nearly ideal from the structural chemistry point of view. It's not a case for cysteine, where here we have 6-member cycle and with angles distorted. But it was worthwhile trying, so we did try it. Results were really disappointing. If we compare with MAG3 complex, which was not a champion in stability, we could see all the signatures of instability, high activity in blood, which means that we have translation to blood protein, and higher activity in stomach and salivary gland, which indicate of presence of reoxidation in the blood and loss of activity from the complex. Definitely no good. Well, it has to be noted that if you place cysteine at C-terminus, then you suddenly could get the same 5-member ring even with cysteine. So there is a difference where you place at N-terminus or at C-terminus. So it was worthwhile trying. So we decided to check it, and we ran a comparison between mercaptoacetyl affibody labeled with cysteine, glycine, 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 and we checked this cysteine-based chelator at C-terminus. We just simply added cysteine to C-terminus and ran labeling. And we clearly could see stabilization, not only to mercaptoacetyl, not only to cysteine on N-terminus, but also compared to mercaptoacetyl-based chelators. And we did imaging, very nice image already 1 hour after injection, some background in the blood pool, which was nearly completely gone by 4 hours after injection. So this in principle worked. So our idea was to see if we can further improve the biodistribution using different amino acids. So what we made, we create a small library. This is 5 members of it. Totally it was 10, but we have very neutral 3-glycine cysteine, GSEC, which is essentially mirror of our best mercaptoacetyl-based chelator, mercaptoacetyl ESE, and we looked at also at influence of charge of amino acids, serine, polar but not charged, negatively charged, glutamate, positively charged lysine. I would say that this variant mirror worked pretty well. We had approximately the same level of kidney activity and low intestine and low liver. Positively charged lysine-containing chelator was the worst. Highest kidney red, highest liver uptake, highest renal uptake. Glutamate behaved decently, serine very decently. The best variant in this case was 3-glycine variant, where low activity in intestines was associated also with low activity in kidney. So we have modified also N-terminus in order to keep charge negative at N-terminus. Here is a result of head-to-head comparison between 2 variants And this is a variant containing GESC. It matches very well its mirror, mercaptoacetyl containing, actually a little bit better, with activity in tumor slightly higher than activity in kidney, and with GGG sequence, we apparently had much higher activity in tumor than in kidney. Actually, later on, we use the same chelator for labeling with rhenium 188, and we have found that in this case we should have dose to tumor at least threefold higher than the dose to liver. So it's possible to kill tumor without destroying kidney. So that was a good example what you could reach by rational design of chelator. So this slide is just an extension of what I have shown you previously, and three additional variants with C terminal cysteine-based chelator. And I really love this slide because it shows how magic labeling chemistry can be. 58 amino acids in this protein are exactly the same. The difference is in 3 amino acids, maximum differences. But suddenly, instead of essentially non-functional imaging probe, you get very, very decent imaging probe. So chemistry labeling chemistry is not only a way for stable attachment of a radionuclide to a targeting protein. It's also a very powerful tool in modifying pharmacokinetics and development of highly sensitive imaging probe. This is important message. Overall, the cysteine-containing peptide-based chelators have a number of advantages. For example, chelator is incorporated during protein production. Essentially, it's built in, it's engineered in. You needn't make an additional coupling step and extra purification. You can use it for both peptide synthesis and recombinant production, which is convenient. You still can modulate complex stability by modifying side chain, and you also modify the biodistribution. Problem is that the labeling conditions are quite harsh. So it's again either high pH or it is high temperature around 90-95 degrees. If your body molecules tolerated, adapts, tolerated, DARPins lost the capacity, refolding capacity, for example. We did try it for DARPin, it didn't work. Well, there are no absolutely perfect things in this world, unfortunately. One good chelator has been developed by Theodosia Meine and Bertolt Nock. It is chelator which nicely used for technetium O2 core, and this is tetraamine chelator. Theodosia has used it for a number of short peptide analog, for example, demobenzine, somatostatin analog, or demostatin, somatostatin analog. Demo because she works at Democritus Research Centrum in Greece. And all of them were based on exactly the same chelator. Room temperature, but unfortunately always very high pH. And we evaluated this chelator for synthetic Fi-body molecules, and we could very clearly see much higher uptake in liver. And there are two negative factors. So we know that it has a positive charge, and we now know that adding positive charge at N-terminus of Fi-body molecules usually is associated with elevated liver uptake. Plus, we have a very strong suspicion that somehow we're losing site specificity, and in very harsh labeling condition. Technetium or can interact also with amide in ore of Fi-body molecules. So that method works for a number of peptides, but not for Fi-body molecules. In early 90s, a new core, 3-carbonyl core, has been discovered essentially by Roger Alberto and Roger Schibley in Paul Scherrer Institute in Switzerland, and this is unique core in that sense that it carry positive, has technetium 1+ oxidation state, and it forms stable complexes with variety of different ligands. So in all this transmutation, 3-carbonyl remains to be bound to technetium, while water molecules can be substituted with a variety of ligands and very different donor atoms, including nitrogen, including sulfur, including oxygen-containing moieties. The most interesting was development of labeling of hexahistidine tags in recombinant protein. This work was published in Nature Biotech. Sorry. I cannot talk here. Okay. All right. So hexahistidine tags or pentahistidine tags are quite commonly used in biotechnology for so-called immobilized metal ion chromatography purification. And well, it's easy in this way purify one desirable protein from large variety of protein which are typically produced by cells. What Weibel has found that technetium tricarbonyl forms complexes with two histidine. And what is important is the motif binding is histidine, then one histidine is not involved in complexation, and then another histidine, HXH. So complex, but it forms stable complex, and so as I mentioned that it was published in Nature Biotech, it's not that easy to publish chemistry in Nature. We did try to apply it for body molecules. And what we have found that we have quite high liver uptake. So kidney we expected to have, but liver was also very clearly visible, and it was brighter than tumor. And since liver is major metastatic site for nearly every cancer, that means that we could not visualize liver metastasis, so value of such tracer would be equal to 0. But we know that it's not a problem of body molecules, because with other more appropriate chelator, we apparently could visualize tumor but not liver. So our problem was apparently in the presence of hexahistidine tag. And later on, we formulated that it's nice, it's site-specific labeling, so we know where in our protein is a label. The same tag is used for purification of a labeling. So very often you have already this tag during your purification step, and so then you just use it. But high liver uptake was undesirable, and we put it aside. Later on, when we start to learn site-specific labeling of body molecules, we got quite shocking results, observing high liver uptake when we had hexahistidine containing body molecules. So, and label was placed at C-terminus in this case. I managed to persuade our biotechnologist, and we indeed have found that if we don't use hexahistidine tag, so activity in liver is reduced quite dramatically, independent which label we put there. Is it indium label or through DOTA, or is it technetium label attached to C-terminal cysteines? So I essentially forced our biotechnologists not to use the hexahistidine, and they started to hate me because its presence simplifies so much of hexahistidine purification. I mean, you put several proteins in robot and it run HPLC overnight, and next morning you have several nicely purified proteins. If you don't have hexahistidine, it's a laborious process. would, for a single cysteine, for a single protein, it would take good biotechnologists with PhD degree 1 week. So it was, well, apparently not good, but on the other hand, we need to have a protein with a good biodistribution profile. By that time, I had already clue that lipophilicity is not good, that positive charge at N-terminus is not good, and hexahistidine is ugly from this point of view. So histidine has pKa of 6.5, so that means that it's either lipophilic or with probability of 10% it has positive charge. All bad features. If you add to this pretty high lipophilicity of technetium tricarbonyl core as such, so it creates quite a bad precondition for biodistribution. What I did try to improve the situation, since I have a big massive of data for biodistribution, I noticed that if you modify N-terminus, effect of modification is much higher than modification of C-terminus. So I suggested to test two variants, just placing hexahistidine tag at C-terminus instead of N. And biotechnologists, for some reason, believe that if you place hexahistidine tag at N-terminus, you improve expression. Actually, that was not the case, but everyone tried to put it at N-terminus. So second variant, as you remember, that it was H histidine X histidine. So I just say, okay, let's substitute every second histidine with glutamate. So we created, instead of H6 tag, tag. And what we figure out, that it's still possible to purify it using IMAC chromatography. So it solved the issue. And it still was possible to label with technetium at N-terminus with reasonable stability. So we created a small library and evaluated them in mice, and it was very, very clear. So simple translocation of hexahistidine tag from N-terminus to the C-terminus resulted in twofold decrease of uptake in kidney, in liver. But if we use tag, so we had more than tenfold reduction. So, and this was very clearly shown in mice. So these mice were injected at the same time and before imaging. So they were euthanized and placed on a collimator of gamma camera, essentially side by side. So an image in the same session. Here you could see very clearly very high uptake of activity in liver, while you don't see such a bright liver in this case. At least tumor is much more bright than liver. So this worked. Next step was to figure out all the factors. Is it lipophilicity? Is it charge? Is it position which play a role? So we collected a number of other variants. So we added lysine, to have the same hydrophilicity as glutamate, but opposite charge. And we also added alanine and isoleucine, so to get tags except he, ha ha ha, and he, which have much higher lipophilicity. What we have found that first, if you look here, that liver uptake was definitely dictated by lipophilicity of amino acids. So here was much lower than ha. Hexahistidine has even higher uptake, and he with the highest lipophilicity has a huge uptake. What was shocking for us at the same time, that very hydrophilic HK tag had, but positively charged, had also very high liver uptake. The second aspect was that the effect of amino acid on C-terminal positioning was much less pronounced. Again, the HK was definitely the worst. There was a tendency to increase of liver uptake with lipophilicity, but it was far not that sharp as it was in case of N-terminal positioning. That is also necessarily to keep in mind when you designing radiopharmaceuticals. So attaching one atom or radionuclide, it means that you attach at least one atom. Most likely it would be group of atoms. So that modify overall lipophilicity, overall charge. But in fact, when working with proteins, the local modification might play much stronger role than overall, because those variants have the same lipophilicity overall and the same charge, but apparently the local effect of modification is much stronger here. So essentially this means that when working with protein-based radiopharmaceutical, you never can work with a single candidate. You need to create a library and evaluate it, because it's not really easy to predict what will be the effect of biodistribution of your labeling. Later on, we have demonstrated that use of tag appreciably improved the biodistribution of antibody molecule for imaging of insulin-like growth factor, which play an important role in many malignancies. And also was improved biodistribution of antibody molecules targeting HER3. That is a bad receptor which might be responsible for resistance to trastuzumab and breast cancer. Still, when we started to work with ADAPT, we suddenly have found that tag is not better. It's worse. comparing with hexahistidine tag. And we just have to think that two factors. First, the stability of complex at He tag is not as strong as with hexahistidine tag. So probably it's hepatic uptake and renal uptake which results in release of catabolites. But also important that N-terminal sequence of ADAPT has a number of amino acids which are either charged or polar next to hexahistidine tag, which probably neutralize its effect. And what we have found that we have quite good tumor uptake using old good hexahistidine tag with rather low uptake in the liver. So it worked, and we also demonstrated that in this case we have HER2 specific accumulation in tumor, because if we pre-saturate HER2 receptor with trastuzumab, so we completely obliterated the tumor uptake of hexahistidine tag. And the latest data, which I hope we will submit for publication next week, it's collaboration with Dr. Chernov and Dr. Bragin and Toms, who demonstrated very clearly that ADAPT labeled with 3-carbonyl using hexahistidine tag provide a nice imaging of HER2 expressing tumor, and we can very clearly discriminate between HER2 positive and HER2 negative tumor. So it influences clinical decision concerning patient treatment. Well, I mentioned that He tag didn't work with ADAPT, but when we start to work with DARPin, we again have evaluated we have again evaluated the influence on hepatic uptake, and here was very clear that He tag reduced more than 4-fold hepatic uptake. So in principle, it's better, but effect depends on protein, and also in mice we could see very high liver uptake in the case of hexahistidine tag, but we managed to suppress it using flocculation He tag. So, taken together, Technetium is the most commonly used nuclide. It's cheap, it has nice imaging properties, it has nice dosimetry properties. Labeling chemistry is not simple per se, but if you master it, you could get a very powerful tool for improving imaging properties of your targeting molecules. Well, that's all for today. Thank you for your attention. If you have questions, you can ask. Если у вас есть вопросы, вы можете их задать, в том числе и по-русски. Ни у кого нет вопросов? То ли предельно ясно все было, то ли я укатал всех.
Есть в чате вопрос.
Виноват, да. Я чат, к сожалению, я должен выключить шеринг тогда. This is an interesting overview of the different technetium chemistry and application. How are the application for a particular molecule determined? Are the first technetium labeled molecules aimed for a determined application, or is it different molecules are first tested in animal models and then seeing the biodistribution in NMR or PET scan? All right. Since question in English, I'm answering in English. The first development was mainly associated with imaging of bone metastasis, and avidity of phosphonates to bones was known before the technetium radiopharmaceuticals has been developed. So it was a wild attempt just to make a phosphonate complex of technetium to visualize the bone metastasis. So what happens in the bone metastasis, malignant cells start to destroy the matrix of bone, and bone try to withstand this by making a fresh hydroxyl apatite, which is constructive material, and that avidly takes up the phosphonate. So in many cases, especially in prostate cancer, if patient has a bone metastasis, it's decisive for making of clinical decision. Because if the cancer is localized, it makes sense to make a curative treatment and hope that patient will be healed. If cancer is disseminated, curative treatment senseless. Patient will not survive it, but you will make his last weeks or months miserable because of chemotherapy or surgery. In this case, bone scan has quite low negative predictive value. So if there is no bone metastasis, you cannot say that there are no dissemination of the cancer. But if there is a bone metastasis, so it's very strong positive predictive value. So that was a history how the technetium started. And it was very much apparent pretty soon that Technetium is an excellent, cheap nuclide for imaging. Cheap does matter. Whatever reaches a society, you need to pay for healthcare. Later development was very often associated with no molecular targeting. For example, well, there was some funny time when there was no CT, and for example, determine the size of liver was impossible. X-ray is not really good for imaging soft tissues. So if you make a colloid with Technetium label, colloid will be taken up by Kupffer cells of reticuloendothelial system, liver and spleen, and so on. You can visualize liver and spleen. For quite a long while, Technetium was used in this rather anatomic or functional image. Well, you could, for example, visualize blood flow in the lung. So if you take macro aggregates of albumin, so that they could go through major vessel and stuck to capillaries. So you label it and they would occupy capillaries in lung proportionally to blood flow. Well, it's mechanic, it's pretty cruel, but if you don't embolize all the capillary in the lung, patient tolerate it very well, but you could see area where the lung perfusion is insufficient. Nice example is, of course, development of imaging probe of sentinel nodes, so beautiful work done in Tomsk as well. On the different variants, so where again colloidal particles were injected close to the tumor, and that permits identification of first draining lymph node. So that permits you to identify it. And if you excise this node, and you can analyze, does it contain malignant cells or not? And if the first draining lymph node does not contain malignant cells, most likely cancer is not disseminated. So it's again give a good rationale to give a patient curative treatment instead of palliative. So alternative is, of course, to excise all the nearby lymph node, but it's debilitating procedure. So typical is whole lymphatic system in breast cancer is excised, so then it's edema all over the hand. Not nice, painful for the patient. So that doesn't work that way. So it's not really a molecular, but so Technetium just give more or less mechanical part, the traceability. You could visualize distribution, you could measure the distribution, and that gives you quantitative information or semi-quantitative information about state of health. Nowadays, it's switched to molecular. In this case, usually you have, one used to visualize targeting conjugate as a consisting from three parts. It's targeting moiety, it might be antibody, it might be peptide ligand to something, some receptor which is overexpressed in tumor. Well, it might be artificial ligand like our scaffold proteins, Amphibodies, adapts, DARPins. So that is function, just find the target and bind to it. And then you have radioactive nuclide with appropriate chelator or linker, depending on the physicochemical properties. And then it's sometimes you need a spacer or linker. And linker plays several roles. Sometimes you need to modify the biodistribution. So, for example, when we work with bombazine short peptide, we use polyethylene glycol to make the whole construct more hydrophilic, so less prone to uptake in liver. And sometimes if you place radionuclide close to molecular recognition site, it might create simply sterical hindrance to recognition. So if you put a spacer, so you have a better chance to have the better affinity and accordingly better accumulation in the tumor. So essentially nowadays one develops the targeting moiety providing molecular recognition, and then starts to consider an appropriate label. And in some cases, it's technetium. If you can do technetium for SPECT, it's always good because it's cheap, it's available. We will see if we can get away with technetium with DARPins. We have shown, though, that if you use iodine label, we can get much better contrast, and I have a strong feeling, Dr. Stasiuk, that we will need to put certain efforts in labeling of DARPins with iodine if you want to have another story of success in Tomsk. I guess it will not miss you with the time. So that is where we are. I would like to understand the rationale behind this tax development. Well, the tags are selected to overall first permit stable binding of nuclide to tumor-seeking moiety. That is always a reason. But second is, as I mentioned, that they can also modify biodistribution. And what I could summarize, it also depends very much on protein, but or targeting protein. But what I could always say that one common feature is that hydrophilic is better than lipophilic, and negative charge on this moiety is better than positive charge. But the degree of such influence might be very much different on the peptide. So, and then I have a question from Dr. Nelson Wheeler. Is there any some kind of research to use technetium 99 together with some beta emitter in theranostics? I would say that there are plenty. In principle, theranostics includes the visualization of a target for making a therapy decision. Strictly speaking, we are not even obliged to use exactly the same targeting probe. For example, visualization of HER2 using ADAPT in our case, and treatment, HER2 specific treatment with antibody Herceptin is also theranostics, though they are very much different. So if we want to treat, for example, classical example now, so treatment of prostate cancer with PSMA binder. Well, apparently lutetium 177 is the best nuclide for therapy, which we have in hand, we as medical and scientific community. We need to ensure that our tumor express PSMA sufficiently. There was a big euphoria about PSMA, but now it seems that expression level is approximately 85%. That means that if you treat everyone, at least 15% of patients would not get any benefit from such therapy. They would suffer side effects. And they are not innocuous. It's xerophthalmia, xerostomia, and it's awful when you don't have lacrimas in your eyes because it's very painful. So we need to identify those patients. Lutetium does not dosimetrically non-sustainable to use beta emitter for selection. So if we have technetium labeled PSMA binder, we can use technetium labeled binder for visualization of HER2 of PSMA expression and selection of the patient, and then treat them with lutetium. One easy case, if it works, is to use rhenium 186 or rhenium 188 instead of technetium, because those are very close chemical analogs of technetium. Well, they are not exactly the same. So rhenium is more easy to reoxidize, but in principle, that might work as well. With rhenium is a bit suboptimal. Both isotopes of rhenium have a bit highish beta particle. Rhenium 188 pretty high. Rhenium 186 a bit lower, but so they are rather better for bulky non-operable tumor than for small metastasis, but they can be used. Any more questions? I don't see any more questions in chat. Well, you have 30 seconds to think about your questions. Otherwise, thank you for your attention.
Большое спасибо за очень интересную лекцию.
Спасибо вам за внимание. Будем надеяться, что мы и дальше что-нибудь осмысленное будем с вами делать. Окей. До свидания.
До свидания.
Так. Сейчас должен завершить. Ну вот, сейчас. Так. Так. Екатерина,
Да.
вопрос номер 1. Для взаимодействия можно я вас буду звать просто?